All right, and we're back. Second podcast here on problems. We just got done talking about Rayleigh scattering, one of the main sources of limitations or attenuation in fiber. Just as kind of a follow-up, this is caused by the metal ions in the silica matrix, your glass matrix. The light rays being scattered as it hits those metallic ions. Those metallic ions act like little mirrors. This occurs most around the 1,000 nanometer wavelength. It's responsible for about 90% of the attenuation. So to avoid that, I should say to minimize the amount of scattering, they avoid that wavelength. That's why you have multi-mode at 850 nanometer, your single mode at 1310 or 1550 nanometer. That's to avoid the majority of that scattering that occurs. Another area of attenuation or problem of fiber is absorption. If you think about, you put a towel outside in the sun. One towel is white, one towel is dark blue. The dark blue is going to feel warmer because it's absorbing more sunlight. Well, as I run light through any material, the material itself is going to absorb some of that light somehow. And that's because of the impurities in the silica. So there is some loss due to absorption. Some of that light energy is getting absorbed and turned into heat. Dispersion. This is another area of problem with fiber optic. As the light is sent into the fiber, it tends to spread out, if you will. And there's two major types, modal and chromatic. Let's talk modal first. The modes of light, multi-mode modes of light, multiple rays of light. As I inject that into the fiber, those rays of light can arrive at the other end at different times. If I look at single mode, it's one single ray of light. There really is no modal dispersion because it's one ray of light. When I get there is when I get there. But when I'm doing multi-mode and I have multiple rays of light representing a pulse of 1, graded index down here, multiple rays of light representing a pulse of 1. Again, we're showing one pulse of light down through the fiber. That is a 1. And that pulse of light is made up of multiple rays of light, multiple modes of light. Well, when I'm dealing with step index, those rays of light could be bounced around kind of erratically, and some of the rays of light get there now, and some get there a fraction of a second later. They're going to get there out of time. Kind of like releasing a group of runners to run around the racetrack. Some will get there first, some will get there second, third, some will get there last. That's just how it's going to be. Well, the same thing happens with light rays. They arrive at the other end of the fiber out of time, and that can cause some timing issues. That's your dispersion. It's not so pronounced in your graded index because the graded index is kind of bending it, massaging it down the core of the fiber from one end to the other. You don't have near as much dispersion, modal dispersion in graded index. That's why graded index is usually used more, kind of preferred more than the step index. So, how do you minimize modal dispersion? Well, one is single mode. There's only one ray of light. Another one is using things like graded index to minimize the amount of modal dispersion. The other type of dispersion you get is chromatic dispersion. Well, chromatic, if you're an instrument player, when you say chromatic, you think chromatic scale, you think of playing every note from A the whole way to G and back again. When I talk light, when I say chromatic, I am thinking our visible light spectrum. When I run light through a prism, it breaks it out into the Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Well, when I run visible light through a prism, it's bending it and breaking it into its component pieces, right? That is a form of dispersion. That is a visible dispersion that we can see. Well, if I run light through a prism, I bend it through a prism, it's going to break it into component pieces, right? So if I start bending light through a fiber, I'm going to start breaking it into its component pieces. So as I'm refracting that light down the fiber, it's going to start dispersing into its component pieces. And the way to control that is with our spectral width. The spectral width talks about kind of the quality of the light source. An LED light source, you say it's emitting 850 nanometer light source, but really it's emitting wavelengths below and above that. It's emitting 840, 841, 842, 843, 851, 852, 853, 854. It's emitting wavelengths below and above that. It's not perfectly and only 850 nanometers. So with my light source, I'm emitting a range of wavelengths of light. So a cheap, inexpensive light source is going to emit a larger range of wavelengths of light. It's going to have a larger spectral width. And the more wider spectral width I have, the more bending I'm going to get and breaking into component pieces. So one way to handle chromatic dispersion is by controlling my spectral width of my light source. LEDs have a spectral width of about 150 nanometers. So I'm transmitting, 775 to 925 nanometer wavelengths of light. Ooh, that's a lot. That's a good range of numbers, and when I start bending that on my fiber, it's going to start breaking into those component pieces pretty easily. Meanwhile, a laser diode, a laser light source, a laser diode has a spectral width of about 5 nanometers. Not many wavelengths of light, so there's not many there to bend into component pieces. There's a lot less chromatic dispersion with a laser diode, a laser light source. But again, I'm going to pay more for that. And here it kind of shows you in graph form, trying to show you a large spectral width versus a small spectral width. And that's all. That's one way to control. Chromatic dispersion, different wavelengths refracted differently. Fiber core gradient index will refract different wavelengths of light differently. And when we'll get to the end at different times. And here it shows you again chromatic dispersion. But here's kind of the telling picture. Your LED light source versus a VCSEL. This shows you your wavelengths, a lot varying range of wavelengths coming out of the LED versus the VCSEL, your laser diode. And this also shows you laser diode, the spectral width. Here you're seeing an 850 nanometer laser diode, very small spectral width coming out of that light source. So controlling your spectral width helps control your chromatic dispersion in your fiber, the amount of chromatic dispersion you get in your fiber. There we go. There's probably more than you ever wanted to know about fiber optic, but there's some of the limitations or technical limitations of fiber optic.